Welcome to Quantum Computing. This is your first lecture. This is your Professor Atif Fareed Muhammad at Marshall University. Let's learn together this new and exciting field. This module provides an overview of quantum computing, its potential impact, and its relationship to classical computing. We will discuss the key differences between bits and qubits, the concepts of superposition and entanglement, and the potential applications of quantum computers in various fields. This module will also cover the history of quantum computing and the current state of the field, including the challenges and opportunities that lie ahead. We will introduce the basic terminology and concepts that will be used throughout the course, setting the stage for a deeper dive into mathematical and physical principles underlying quantum mechanics. Let's begin. Imagine if your computer could try every possible answer to a problem at the same time. Instead of checking them one by one like a regular computer does, that's essentially what quantum computing does, using weird but real properties of the quantum world. Regular computers store information as bits that are 0 or 1, like light switches that are either off or on. Quantum computers use qubits that can be both 0 and 1 simultaneously. Thanks to the phenomenon called superposition, kind of like a coin spinning in the air that's both heads and tails until it lands. This allows quantum computers to process millions of possibilities in parallel, making them incredibly powerful for certain types of problems. Let us look at a practical example of this. Imagine you are trying to find your friend in a massive maze with thousands of paths. A regular computer would have to explore each path one at a time, which could take forever. A quantum computer using superposition could explore all the paths at once and find your friend much faster. This makes quantum computers especially useful for problems like cracking complex codes, discovering new medicines by simulating how molecules interact, or optimizing delivery routes for thousands of packages. While they won't replace your laptop for browsing the internet or playing games, quantum computers could revolutionize fields where we need to sort through enormous amounts of possibilities to find the best solution. So, in reality, solving problems faster than classical computers is where the quantum computing shines. Why quantum computing? That's a very interesting and intriguing question. Classical computers, despite their incredible speed and sophistication, face fundamental limitations when dealing with certain types of problems. The biggest challenge is that they process information sequentially. They can only check one possibility at a time, even if they are doing it incredibly fast. When problems grow in complexity, the time needed to solve them can increase exponentially. For example, breaking a 256-bit encryption code would require a classical computer to try so many combinations that it would take longer than the age of a universe to crack. Even if we used the most powerful supercomputer available today, similarly simulating the behavior of just 300 atoms interacting with each other would require more memory than exists in all the computers on Earth combined. because classical computers must track every possible state of the system individually. This exponential scaling problem means there is a whole category of important problems that classical computers simply cannot solve in any practical time frame, no matter how much they are improved over time in terms of the hardware. These limitations become especially apparent in fields like drug discovery, artificial intelligence optimization, and cryptography. When pharmaceutical companies want to simulate how a new drug molecule will interact with proteins in the human body, they must make simplified approximations because modeling the full quantum behavior of all the electrons and atoms involved is beyond classical computing research. Financial institutions trying to optimize investment portfolios with thousands of variables, or logistics companies planning optimal routes for massive delivery network hit similar walls where the number of possibilities explode beyond what classical computers can handle efficiently. Quantum computers sidestep these limitations by leveraging quantum phenomena like superposition and entanglement, permitting them to represent and process multiple states simultaneously. While classical computers will always be better for everyday tasks, their inability to efficiently solve these exponentially complex problems is precisely why quantum computing represents such a revolutionary leap forward for specific but critically important applications. Simulating molecules for drug discovery, as I just mentioned, is an example for you to understand. Classical computers, despite their incredible speed and sophistication, face fundamental limitations when dealing with certain type of problems. As we have just discussed in quite depth, the classical computers are built on a surprisingly simple foundation, the bit, which is the smallest unit of information that can only exist in one state out of two at a time, either 0 or 1, like a light switch that either is off or is on. Everything your computer does, from displaying this text to running complex video games, is ultimately just billions of these bits being flipped on and off in every specific pattern. These bits are manipulated using logic gates, which are like tiny decision makers that follow strict rules. For example, an AND gate only outputs a 1 if both of its inputs are 1. By stringing together millions of these logic gates in clever ways, classical computers can perform incredibly complex calculations. However, they do this by following a linear step-by-step process. The computer reads an instruction, executes it, stores the result, and then moves to the next instruction. The sequential processing is both the strength and the fundamental limitation of classical computing. The architecture of classical computers has remained remarkably consistent since the 1940s, following what's called the von Neumann architecture. In this design, there is a central processing unit or CPU that does all the calculations, memory that stores both data and instructions, and a bus that transfers information between them. When you ask your computer to solve a problem, it breaks the problem down into millions of tiny steps that can each be represented as operations on bits. For instance, adding two numbers involves a series of logic operations on the binary representations of those numbers. While modern processors can execute billions of these operations per second, they are still fundamentally checking one thing at a time. This means that as problems get larger and complex, the time needed to solve them grows proportionally, or worse, exponentially, for certain types of problems. So that's how we deal with the standard classical computing as per our current understanding. So before I introduce the qubits, let me finish the thought that I started. So this is where quantum computing offers a radically different approach. While classical bits are always definitely 0 and 1 or 1, quantum bits or qubits can exist in superposition simultaneously, representing both 0 and 1 until they are measured. Additionally, qubits can be entangled, meaning the state of one qubit is directly connected to the state of another, even if there is or there are physically separated, or there is a physical separation between those. These quantum phenomena permits quantum computers to explore multiple solutions in parallel rather than sequentially. For example, while a classical computer with 3 bits can only represent one of 8 possible combinations, 0, 0, 0, next could be 0, 0, 1, next could be 0, 1, 0, and the list can go on. At any given moment, a quantum computer with 3 qubits can represent all combinations simultaneously. This parallel processing power grows exponentially with each additional qubit, which is why quantum computers can potentially solve certain problems, like factoring large numbers or simulating molecules interactions millions of times faster than the most powerful classical supercomputer can do. So as mentioned, qubits are 0, 1 or both, that is superposition. Spinning a coin heads and tail simultaneously. So if you flip a coin, it goes into the air, it comes either 0 or 1, head or tail. What if it stands? Think about it. That's a great question. Understanding superposition, let's look into this with an example. Superposition is one of the most mind-bending concepts in quantum mechanics, and it is what gives quantum computers their extraordinary power. In the classical world, things are always in one definite state. A coin is either heads or tails, as mentioned earlier. A light is either on or off, and a bit is either 0 or 1. But in the quantum world, particles can exist in multiple states at the same time until they are observed or measured. Think of a qubit like a coin spinning in the midair. While it is spinning, it is not really heads or tails. It is both simultaneously. Only when you catch it and look at it does it collapse into one definite state. This is not just our lack of knowledge about which state it is in. The qubit genuinely exists in both states at once, with different probabilities. For each outcome, a single qubit is a superposition represents both 0 and 1 at the same time. 2 qubits can represent all 4 combinations, so 0, 0, 0, 1, 1, 0, 1, 1, simultaneously. And 3 qubits can represent all 8 possible combinations at once. This property of superposition is what allows quantum computers to process information in parallel on a scale that classical computers cannot match. When you put multiple qubits into superposition and let them interact, the quantum computer can essentially explore many different solution paths at the same time. For example, if you're trying to solve a maze, a classical computer would have to try each path one by one. But a quantum computer, as mentioned earlier, in superposition can explore all paths simultaneously. However, there's a catch. When you measure the qubits to get your answer, the superposition collapses and you only get one result. This is why quantum algorithms must be carefully designed to amplify the probability of the correct answer while reducing the probability of wrong answers, so that when the measurement happens, you are most likely to get a solution you're looking for. It is like conducting an orchestra where all instruments play different notes simultaneously, but they are arranged so that the right notes reinforce each other and create clear melody while the wrong notes cancel out. Schrodinger's cat is a phenomena that we will be discussing in quite depth, where Schrodinger, who was a scientist, did this experiment and put a poison in a box which was supposed to get released over time, and then he pushed the cat and closed the box. Now, at this very moment, even though it is a cruel example, but to understand the quantum computing, at this very moment, cat is either alive or dead. However, we have no clue of cat's state, alive or dead, because a cat can be either living or dead. Dying is a process where you're still living. So we'll discuss this in quite depth in the industrial setting that we will be working with in quite depth. Superposition in action, graphical representation of a qubit in a block sphere. Qubits as a sphere. Let's look into that. What is a block, or B-L-O-C-H? A block, B-L-O-C-H. Sphere is like a special globe that helps us understand how a qubit works. Imagine a basketball where the top of the ball represents 0, like the regular computer bit being off, and the bottom represents 1, like a bit being on. Is a normal computer. So in reality, if you take a basketball and put a black dot on the top, as in your hand, and a black dot on the bottom, that becomes 0 and 1. In a normal computer, your bit would always be stuck at the top or bottom. It is either off or on, nothing in between. But with a qubit, it can be anywhere on surface of that basketball. If the qubit is at the very top, it will definitely be measured as 0. If it is at the bottom, it will definitely be measured at 1. But there is a cool part. If the qubit is somewhere in the middle, like the side of the basketball, or any given side, it's a mix of both 0 and 1 at the same time. A qubit right in the middle has an equal chance of being 0 or 1 when you measure it. When scientists do operations on a qubit, they are basically spinning or rotating it to different spots on this imaginary basketball. And when they finally measure it to get an answer, the qubit snaps to either a top or bottom based on where it was positioned. The sphere helps scientists picture what is happening to their qubits, kind of like how a map helps you see where you are in the world. The power of entanglement. Now that's a good question. I would strongly suggest you to think about entanglement in your best understanding. Let's jump into this. Entanglement is one of the strangest and coolest things in quantum physics, and Albert Einstein famously called it spooky action at a distance because he found it so weird. Imagine you have a pair of magic coins that are entangled. When you flip one coin and it lands on head, and the other coin, no matter how far away it is, even on the other side of the universe, will instantly land on the tails. It is not that the coins are sending secret messages to each other, they are connected in a deeper way that scientists still find mysterious. The coins don't decide what they will be until you look at them, but once you check one, you instantly know what the other one is, even if your friend is holding it miles away. With qubits, when they are entangled, measuring one qubit immediately affects the other entangled qubit, and their states are perfectly correlated. It is like they are twins that are always doing opposite things or always doing the same thing depending on how they are entangled or they were entangled. Entanglement is super important for quantum computers because it allows qubits to work together in ways that regular bits never could. When you have multiple qubits that are entangled, they can share information and influence each other instantly, which helps the quantum computers solve complex problems much faster. Think of it like a team of dancers who are so perfectly in sync that when one person moves, everyone else responds instantaneously without needing to watch or communicate. They just know. This is what makes quantum computers so powerful. For certain tasks, the entangled qubits can explore many possible solutions together as a coordinated team, rather than working independently like bits in a regular computer. Scientists use entanglement to create quantum algorithms that can crack codes, search huge databases, and simulate how molecules behave in ways that would take regular computers thousands of years to figure out. Real world entanglement is quantum teleportation, secure communication. So, here I suggest you to conduct a little research what quantum teleportation is and how we can utilize that in our everyday. This is a thought process, this is a research area that I strongly suggest you to look into. Secure communication, if we align entangled qubits, can we create a message which is secured at both ends, not with private key or the public key. Quantum gates versus classical gates. Comparison is AND gate or gate versus Hadamard or CNOT gates. Flipping a qubit with a Hadamard gate is our understanding of quantum gate. Let's have a little deep dive in this specific topic. Since we all are in computer science, I'll not discuss AND or CNOT gates, rather Hadamard gate, or also known as H gate, is one of the most important and commonly used quantum gates, and it is known as superposition gate because that's exactly what it creates. Imagine you have a qubit that is definitely in the zero state and it is sitting at the top of the block, as mentioned earlier in terms of the basketball, the side of the sphere. Putting it into a perfect 50-50 superposition, both 0 and 1 at the same time, it is like taking a coin that's showing heads and then spinning it in the air so it's both heads and tails simultaneously. If you apply the H gate to a qubit that is in one state, in the one state, not the zero state. It also creates a superposition, but with a slight difference in what's called a phase, which affects how qubits interact with each other. The H gate is reversible too. If you apply it twice to the same qubit, you get back to where you started from. The H gate is super important because it is usually the very first step in most quantum algorithms. Think of it as starting gun that gets the quantum computation going. At the beginning of the quantum program, your qubits are usually all in the zero state, which is not very useful because they are not taking advantage of any quantum properties yet. By applying H gates to your qubits, you put them all into superposition, which means they can now explore multiple possibilities at once. This is where the quantum computer's parallel processing power comes from. So hope this has given you an understanding how we apply standard computer science gates to a quantum superposition in terms of quantum gate. And let's go and learn more. So flipping a qubit with a H gate is a great example. Building quantum circuits, the basics of quantum circuits, and simple circuit diagram. This is something that I would suggest you to conduct a little reading, available anywhere on Google Scholar or IEEE Explore, and see how the basics of quantum circuits get you to an understanding or an appreciation of a simple circuit diagram in standard computer science. Famous quantum algorithms, we'll be looking into Shor's algorithm, which is factoring. We'll also look at Grover's algorithm, which is searching. The example is breaking encryption. You all might have heard breaking Bitcoin. That will happen with quantum computer eventually. Where can quantum computing help? Drug discovery, as mentioned earlier, optimization, route optimization, inventory optimization. The cryptography is another one. How to be in sync, another one. Faster database searches, so you don't have to go line by line. You can go in one single throw, get the answers. The final state that you're looking for. Quantum computing and security, threat to classical encryption. We'll be discussing this in quite depth. Example is RSA encryption vulnerability when quantum computer kicks in using the H gates. At the same time, figuring out what can be cryptic security that you have applied. Solving complex problems, traveling salesman problem. I would suggest you to read into what is traveling salesman problem and how to establish an idea of using standard computer science or standard computing to solve that. The route optimization for delivery trucks is another area that is solving the complex problems kicks in terms of utilizing the quantum computing. Simulating the nature, modeling molecular structure for the drug discovery, for the molecule interactions to create a personalized drug, for solving some sort of vaccination issue. Example can be designing new materials in terms of getting our sicknesses eradicated. Quantum machine learning is a full area in its own capacity. Since we are discussing introduction to quantum computing, I would suggest you to start reading on this. So in future, when you would like to go and conduct research, it'll be helpful how you will be incorporating quantum theory or algorithms in the machine learning. The speeding up AI training can be assisted by quantum machine learning. Image recognition can be faster when quantum machine learning is utilized. A brief history. The timeline of quantum computing is Feynman in 1982 to present, and IBM's first quantum computer. Let's look into this in a little bit more depth. The idea of quantum computing started in early 1980s when a famous physicist named Richard Feynman suggested that regular computers would never be able to simulate quantum physics properly because they don't follow quantum rules themselves. He proposed that we need to build computers that actually use quantum mechanics to do calculations. In 1985, another scientist named David Deutsch described what a universal quantum computer would look like and how it could solve certain problems that regular computers couldn't handle. Throughout the 90s, researchers made exciting breakthroughs by inventing quantum algorithms, special step-by-step instructions for quantum computers. The most famous was Shor's algorithm in 1994, which showed that quantum computer could break the encryption codes that protect our online banking and secret messages much faster than any regular computer. This got government and tech companies really interested because it meant quantum computers could be both incredibly useful and potentially dangerous if they fell into wrong hands. Building an actual working quantum computer turned out to be incredibly difficult because qubits are extremely fragile and sensitive. Even the tiniest vibration, heat, or stray electromagnetic wave can destroy the delicate quantum state. In 2016, IBM made history by putting the first quantum computer on the internet for anyone to use, called the IBM Quantum Experience. This first version had just 5 qubits and had to be kept at temperature colder than outer space near absolute zero, which is minus 273 degrees centigrade, to work properly. While 5 qubits might not sound like much, it was revolutionary at that time because there was absolutely nothing prior to that. Students, researchers, and curious people around the world could write and run real quantum programs without needing a multi-million-dollar lab. Since then, IBM and other companies like Google have built increasingly powerful quantum computers with dozens or even hundreds of qubits racing toward the goal of quantum supremacy, the point where quantum computers can solve practical problems that regular supercomputers simply cannot handle. The key milestones, as mentioned, 1994 Shor's algorithm, which I just shared with you as a synopsis. 2019 Google's quantum supremacy, and Google's 53 qubit processor that came later on. Quantum computing today, major players IBM, Google, and Rigetti, IonQ, Sandbox AQ, and then IBM Quantum Experience, as I discussed earlier. Let's continue in the next lecture.